In this video, we're going to take a look at the last topic for circuits, and that is circuits with resistors and capacitors in them. We call these RC circuits. And in particular, what we're going to be looking at is what happens in the circuit while the capacitor is charging up, or if you start with the capacitor charged, what happens as the capacitor discharges. So to start with, we'll take a look at charging a capacitor. I'm here looking at this page in your packet. And it says charging, discharging capacitors. You say, what I have here is I've set up a little circuit, all right? And in this circuit, you see that we've got a battery here, okay? And I've got my high V side, the long line, high V side of the battery, my low V, high potential, low potential. So there's a delta V across the battery. Now, the symbol that oftentimes gets used for kind of that idealized voltage in a battery, so like ignoring internal resistance, that's the EMF symbol, the electromotive force, which is again like a synonym for delta V. Now, every circuit is going to have some resistance, either because the wires have resistance in them just naturally, or there's something that's got a lot of resistance in the circuit, or just the battery itself has resistance, right? And so what we're going to do is we're going to take all the resistance in the circuit, and for this diagram, we're just lumping into one resistance value here, okay? So that's the total resistance in the circuit. And then over here, we have a capacitor on the left side, okay? And now this capacitor is going to start off being uncharged. It's going to be neutral at time 0, and we're going to go ahead and flip the switch here, and we're going to close that switch, which will make a connection, and then the capacitor would start to charge up. So what will happen then, you say, well, I know what's going to happen. In reality, I know that electrons would flow out from this negative V side. They want to get around to the high V side, right? This is a low V, so electrons would start to flow this way. And on the other side, you say, hey, this neutral plate, electrons are going to want to attract into the positive high V side of the battery. So I'm going to get electron flow this way. But we remember that they defined the direction of charge flow before they knew about electrons, and they assumed it was the positive charges that were moving. And so that means even though the electrons are going to start flowing in a counterclockwise direction in the circuit, officially the current is going to flow clockwise. Okay, so my current will be flowing around clockwise. All right. So what's going to happen at first is this is nice and neutral, and here is this high V part of the battery. And so electrons are going to start popping off of the lower capacitor plate and heading to the high V side of the battery. And so that means that this plate will start to charge up positively, right? And the plate up above is where electrons are racing around to it from the low V side of the battery, right? And they're running around, and electrons will start piling up on that upper plate. So at first, you'd say there's no change in potential between the two sides of the capacitor, right? They're both neutral to start with, right? But as time goes on and more charges go in, that's going to affect the delta V across the capacitor. And what will happen is, as I put more and more negative charge on this plate, the V value here goes down, right? My electric potential will drop, right? And as I pull more and more electrons off of this plate's V value will go up. Now, at first, right, when I first turn this thing on, you say, hey, this battery, there's a high V here, and there would have been a lower V, a neutral plate here. And you see, but as electrons get pulled off of this lower plate, the V value goes up, until the V value here and the V value here, right? The V value of the lower plate would be the same as the V value of the high V side of the battery, right? At that point, you're not going to get any more flow because there's no reason for charges to go one way or the other way if they're both at the same V. Do you remember that if there is a delta V, that means there must be an E field, right, between the two positions you're measuring delta V for, right? And an E field's got to have a component that's parallel to the path between the two positions that you're measuring the delta V for. And so in this case, if the delta V is 0, well, then that E field running down the wire would be 0 at that point. Okay, once the capacitor is fully charged. That's how you know it's fully charged. And you say on the other side, you say electrons are going to be moving from the low V up to this higher neutral location here. And so as electrons flow around, start piling up on this plate, you say eventually the V value there will be getting lower and lower. And eventually the V value on this low side of the plate will be the same as the V value on the low side of the battery. And then the delta V there would be 0, right, along this wire, right? If delta V is 0, then there's no E field along that wire, and the charges would stop flowing at that point. Okay, and at that point, again, the capacitor is fully charged. Another way of thinking about it, instead of thinking about electric potentials and energy per charge and saying, oh, well, if the delta V eventually is going to go to 0 and the current will stop. But another way of thinking about it is to think about just the electrons and force, right? You say at first, these electrons are being pushed to go to this upper plate, but as more and more negative charges get there, wouldn't they make it harder and harder to push more electrons on? Electrons don't want to be cooped up near each other. And you say eventually there'll be so many electrons on this plate that it will repel any more electrons from coming in, right? And it'll have some, final charge, negative Q on that plate. And this plate will be plus Q. And so eventually there's so much positive here that I won't be able to pull electrons off it anymore. And so at that point, the current would stop. And the capacitor is fully charged. Let's see. What else can I tell you about this? And so what that means is, as it gets harder and harder to push charges around here to the capacitor plates, that means the current gets smaller and smaller and smaller. And so my current is changing over time. And so that's going to make this a trickier sort of thing to analyze than the problems that we've just been doing. So bottom line here is when the circuit is first turned on, when I first flip this switch, there's no charge on the capacitor plates. And so it lets the first charge, can rush around to that, and the capacitor doesn't fight it at all, right? And I can pull first electron off this plate, and it's really super easy. And so we're going to say that at that first instant, I can push charges in the circuit and the capacitor isn't fighting against it at all. So it's like that capacitor, it's basically like the capacitor wasn't there in a sense, or like the capacitor, you could think of it as acting like just a bare wire that goes straight across, right? It doesn't resist the flow. The current would just flow right through. In this case, it's just flowing and collecting on this plate and flowing off the lower plate. But the point is, it's not resisting the flow at all in the first instant. Eventually, there'll be so many electrons on this plate and so many missing electrons, so much positive charge on this plate, that more electrons won't flow to it at all. And then we'll say the capacitor is fully charged. And so at the end, right, we say that that capacitor acts like a break in the circuit, right? And so I'm going to get no current to it. So it starts like a bare wire, ends as a break in the circuit. That's what happens with the capacitor in a circuit you were charging it. Eventually, that V value of this high V side of the battery, all this will end up being the same V when we're done. Okay? And if I look at the low V side of the battery for this case, you would say, well, here's that low V side. All this, right? You're like, okay, I'm traveling along, right? You say, but wait a minute, aren't I going to lose energy when I go through the resistor, right? Well, the thing is, at the end, there's no more flow through the resistor. And that means there must not be an energy change. So this is all at that same V value. So in this case, it looks like the capacitor, the delta V across the capacitor, is the delta V between red and purple. That's the same as the delta V of the battery between red and purple, right? So this EMF, right, is the same as the EMF, the voltage for the capacitor at the end. But if I skip here to this next page, this says the transient behavior of a charging capacitor. That's the behavior as it goes from one state to the other, as we're going from being uncharged to charged. And to say what we'd really like to do is be able to calculate the charge at any point in time. How much charge is on the plates here, right? On that lower plate, I should say, there'll be a certain amount of positive charge on the lower plate and a certain amount of positive charge on the upper plate, right? But that's changing over time. So I'm going to call that little q. Okay, I'm going to use big Q for like the maximum charge that's at the end when it's fully charged. But I'm going to use little q. It's just a variable that's going to be changing with time. All right. So at the end, I'm going to have a plus q on the lower plate and a minus q on the upper plate. That q, I'd like to know how big that q is as a function of time. I'd love to be able to find the current that's flowing as a function of time. The delta V across the capacitor, right, from one side to the other side, right? If I hooked up a voltmeter here and parallel across it, right, what that voltmeter would read, that's the voltage of the capacitor. I'd love to also be able to find the voltage across the resistor as a function of time, right, from one side to the other side of the resistor. Delta V is a negative integral E dot dr, right? Going along the wire from one spot to the other, right along that path. And you say, well, eventually, the delta V between the top plate, say, and the low V side of the battery, or between the high V and this, that delta V is approaching zero, right? Between here, right, and here, yeah. And so the field pushing it gets smaller and smaller. That last little bit of charge, right, to get the last little bit on, the delta V is so small, the E field is so weak that that last little bit of charge is going to take, forever to get there. So what that means is that the graphs are all going to be these cool asymptotic graphs, right? And so if I think about this, the charge on the capacitor, right, at the start, you say, well, in this case, say at the start, how much charge is on the capacitor? We're starting with it being uncharged. And so at start, the Q is 0. Eventually, that capacitor is going to be fully charged, right? So in this case, I need the same V value all through here, right? It's just the V value of the low V side of the battery, and the same V value will be all through here. That's the high. So the delta V from here to here is the same as the delta V from here to here. In other words, the voltage of the capacitor will be the same as the voltage of the battery in this case. And so I can just fill that in down here, the voltage of the capacitor. At the start, the two plates are neutral, and so there's no delta V across the capacitor. At the start, the delta V for the capacitor is going to be 0. But eventually, it'll be equal to the EMF of the battery. Now, if you want to be picky about it, technically it depends if I'm going one way or the other way, whether I'm going to be going down voltage or up voltage, but the magnitude will be the EMF of the battery. The current, though, the charge at the end, then, right? If I know at the end the voltage of the battery is this EMF, and I know the capacitance, did I say voltage of the battery? Voltage of the capacitor is this EMF, and the capacitance is this big C. You say, wait. We have a formula for capacitors. We know capacitance is the charge per volt. Or I could rearrange this and say that the Q would be equal to the capacitance times the voltage. In this case, at the end, the voltage is the final voltage, that maximum EMF is just the EMF of the battery at the start. So at the end, the Q at the end, which is Q max, which oftentimes I just use a big capital Q for, that's going to be the capacitance times the EMF of the battery, right? The voltage that's going to be set up across here at the end is the same as this voltage for this circuit. So I know how to calculate that Q max. What about the current flowing then? You say, well, the way I find the current goes like this. At the first instant, okay, at time 0, what's the current going to be that flows to the capacitor? Well, that's what flows through the resistor, isn't it? And so here's the way to think about that. I know that for a resistance, right, I can say that the delta V is IR. I use Ohm's law. And so my current is going to be the voltage across the resistor from one side to the other side. If I hooked up this voltmeter, right, times, delta V is IR, so I is delta V over R, right, divided by the resistance of the resistor, right, the resistance of the circuit. So if I set it up like that, you say, well, wait a minute, do I know what the voltage is going to be across the resistor? Well, here's the thing. If you go by the loop law, you know that I trace a path around the circuit, right? Maybe I start, you can kind of do it either way you want. Maybe I start the low V side of the battery, and I'm going to trace around until I made a complete loop. And then the delta V's have to add up to 0. So I'm going to go up voltage here first. How much? EMF, right, of the battery, right? We're assuming the battery's voltage is constant, right? That's what a battery's job is, probably delta V between the two materials in the battery. So I go up EMF. Well, then by the time I make it all the way back around to here, I better have gone back down by that much voltage. And so my delta V for a complete loop is 0. So because potential energy being a property of location or going back to the same location, the change in the potential energy per charge is going to be 0. Because I'm back to the same location, same potential energy there. Okay, so going up EMF, I better go down EMF here. But at the start, at the first instant, there's no charge on the plates yet. So there's no delta V across the capacitor. You say, but wait, if I go all the way around, the delta V's got to be 0. So I go up EMF here. I'm going to go down EMF from one side to the other side of the resistor. Because certainly if I'm going to flow through this resistor, I'm going to dump energy. There'll be a delta V here. And so the delta V for the battery is equal is across the resistor, they say, and there's no delta V across the capacitor at the first instant. Now, as soon as I start getting charges built up here, there's going to be a delta V between the two plates. But at the first instant, there's going to be no delta V across the resistor. I mean, across the capacitor. I'm sorry. There's no delta V across the capacitor. And so that means that full delta V has got to be across the resistor. So the voltage across the resistor at time 0, you say that's got to be, or if you like, delta V resistor naught, you say that's got to be, and actually, if you want to think about it, it's going down, right? If we go, as I go around the loop, if I go up potential here, I'm going to be going down potential as I go through these other parts. All right. So that's the delta V for the resistor at the start. At the end, when this capacitor is fully charged, no more charge is going to be flowing to it. Well, then will any charge be flowing through the resistor anymore? If there's a break in the circuit here, right? That's what a capacitor at the end acts like. You say, well, then there's no more charge flowing through the resistor. No charge flowing through the resistor, that means the current through the resistor is 0, right? And if there's 0 current through the resistor, then the delta V across it has to be, by this formula, if I is 0, the delta V is going to be 0. Again, resistance is a property of the material and the shape of the wire, when it's made out of, the cross-sectional area and the resistivity and stuff. Anyway, those are properties that are constant while the circuit's running. And so if they're constant values, right, is stamped on the side of the resistor, it's marked to say what the resistance is, then that's not changing. So if the current goes to, if the delta V of the resistor goes to 0, then the current's better be 0. And that's it. So at the end, you say the current is going to be 0. I at infinity is going to be 0, right? So what about the start, the first instant? Well, the first instant, we go around, we go up EMF. There's no delta V over the capacitor plates yet. There's no charges on them. We're going to go down EMF going through here. So it's just going to be opposite. So the delta V is opposite the voltage. So how do I find the current? I use Ohm's law. I take that delta V at the end. That's just going to be, at the start, that delta V across the resistor is just equal to the EMF of the I is EMF over R. So my initial current, right, is going to be just EMF over R. Okay, which is what we would get from Ohm's law if that was just the resistor with the battery, right? So at the first instant, this capacitor isn't fighting the flow of charge to it at all. It acts like essentially a bare wire in the sense that it's not affecting the delta V at all. So last thing, delta V of the resistor at the end, we said that's got to be equal to 0. Why? At the end, there's no more charge flowing. If the I is 0 and R is a constant, right, it isn't changing, the delta V better be 0. So at the end, we can say the voltage of the resistor at the end is 0. Okay, and I'm going to call that delta V for the resistor at infinity or something. Delta VC at the start. This is my delta V for the capacitor at infinity, right? right? I might very well mark that like negative EMF because I'm going down. All right, what do you think? So what we have here is we've listed out our initial conditions and our final conditions, right? Showing where things are starting and where things are going to end up. How are they going to get there now? If I drew these graphs, you say my charge on the capacitor plates start at 0, right? And they're going to get more and more charge on the plates, but there's some final value that they're going to approach, right? So it's like, look, here's the, say right here, say this is the maximum Q, right? That's big Q there, right? Then my charge on the plates is going to approach it, and it would take forever to actually fully get that guy charged up and get the full charge on. Now this max Q max, you know what that's equal to? That intercept. Look, it's equal to capacitance times the EMF of the battery, right? Okay, for this circuit, that's what it looks like. So I have this horizontal asymptote. What about the current? Well, it starts off flowing very easily, but then as it starts to pile up the charges on it, again, it's going to slow the current down. And so you're not surprised at all to say, look, there was some initial current, right? Which we calculate over here. By the way, that was equal to EMF over R, right? Yeah. Okay, so there's that initial current. And you say, well, it's going to drop to 0, right? But it's going to take how long? You say, well, technically forever to push the last little electron off. To get the last little charge to the plates, right? You say last one is going to take the force pushing it gets smaller and smaller and smaller. The E field gets weaker and weaker and weaker as the delta V approaches 0, and I get less and less pushing the charges to the plates. And so the last to fully charge the capacitor is going to take forever. And then this trickle of charge flowing to it. So that's the idea. Hey, and we got the initial value. This is what the graph looks like. This is a horizontal asymptote at 0, right? Delta V for the capacitor. You see at first, there's no charges on the capacitor plates, and so the delta V for the capacitor is going to be, you should be saying 0, right? Oh, look, I got it written right over there, yeah? And you say, but it's going to approach some final value, right? And you say, hey, that final value for the capacitor, we figured that out before. We said, hey, at the end, delta V for the capacitor at the end is just going to be minus the EMF of the battery. So maybe if I want to be really picky about that negative sign, then really this graph is just flipped, flipped upside down under the axis here. So I'm going to invert this graph. So really, you could draw it if you wanted, like this, right? Approaching some final asymptote. Okay, let's get rid of this top part. A lot of times they will just draw it like this, or just take like the absolute value of it or the magnitude of it. A lot of times when you see stuff being done with this, but in reality, it's flowing the opposite direction now. So the voltages should be negative. They're going the other way. But that's the idea. Maximum voltage is negative EMF of the battery, right? Okay. What about the voltage on the resistor? You say, well, at first, there's this, when I put first close the switch, the electrons can flow very easily to this. I'm getting a lot of flow through this resistor, and so I'm going to get a big delta V across the resistor to start with. But we know that eventually, as charges build up, my flow gets less and less and less. If the current goes to 0, delta V is IR. As the current approaches 0, then the delta V approaches 0, right? Must not have a good delta V for that. So at the end, so this is going to start off with some flow or voltage across the resistor. And I could even mark that value. You say that would be delta V is IR. That's just the initial current times the resistance. But then as it discharges, it ought to kind of taper off, right? One of these exponential decay type graphs. All right. So the point is that we can logic through what's going to happen in the circuit, what these graphs are going to look like, and we can label like the maximum values and stuff, right? We can jot to figure out what these values are. And so the point is, this page, this is most years on an AP for response problem involving an RC circuit. Understanding this stuff for charging, and then we'll do the page for discharging. If you understand this stuff, how it works, and can set the initial and final values, you can sketch the graph, you're probably getting like 80% of the points, at least, in most cases, on these for response problems on AP. But we do want to be able to do more. We would love to be able to calculate the value at any point in time along this curve, right? And so we got to do some math for that. I got to do a little bit of calculus. I think I'm going to come back and do that. Yeah, let me do that in a separate video.